Hi, I'm Sabir Ahmed. Welcome you to all to the course Computational Finite Difference Method, and this is the introductory lecture. So I'm Sabir Ahmed from the Department of Mathematics, Ahsanullah University of Science and Technology from Bangladesh. Okay, so I think this is the first course here in internet uh, which will provide you computational method or computational idea of finite difference method, how you can compute it, how you can do that numerically in MATLAB using the finite difference method. Okay, so basically this lecture will cover you the basic thing of finite difference method, why we do use that, and what is the basic concept of finite difference method and something like that. Okay, so before going through this lecture, I would like to say something about this course. Like, you must have some basic requirements to go through this, or if you want to understand properly for this lecture. Okay. So if you know linear algebra, especially matrix and linear equation solving techniques, that would be really very great advantages for you, because matrix and linear equation solving techniques are very important for this, because we will have hundreds, even thousands of equations that would be solved, or that must be solved by this technique. Okay, for computational method, in this course I'm gonna use MATLAB because it has a very powerful functions, and it has a wide options to explore. Okay, if you do not have any prior experience of this, and for linear algebra, I would like to recommend you to go to Khan Academy, because there uh, they have the ordinary differential equation lectures, they have PDE, partial differential equations, and they do also have linear algebra basic. Okay, so for primary knowledge of MATLAB, if you do not have an knowledge of MATLAB, then I would like to recommend go to www.youtube.com/user/Sabir Foundation, where you will find MATLAB tutorial for sciences. Okay, I have made several videos uh, for MATLAB, basic MATLAB tutorial for science students over there, so you can explore them. And I have put several examples for you over there, so you can get an idea about how to write code, and how to write your problem, how to solve various scientific problem over there using MATLAB, so you can get idea over there. Okay, so you must have to have a linear algebra and primary knowledge of MATLAB, and if you do have ordinary and partial differential equations here, so it'd be very great advantage for you all. Okay, so before going through this, I would like to also apologize about my English speaking, because I am not a native English speaker. I'm from Bangladesh. Okay, and English is not my mother tongue, so I might make some wrong or fault, or sometimes my accent may be awkward. Please do not mind all about that, because I do believe that language cannot be a barrier for sharing our knowledge. Okay, if I know anything, that must be shared, right? So language cannot be a barrier. Okay, thank you. Okay, let's get started. Okay, so numerical methods. What is numerical methods? Numerical method is another important method or important ways to solve our practical or real life problems that cannot be solved analytically. In that cases, we do use numerical methods. There are lots of numerical methods here. Uh, for example, here finite difference method, finite element method, finite volume method, spectral method, boundary element method, analytical method, discrete element method, mesh tree method, and so on. There are lots of methods, but three methods are very much popular here: finite difference method, finite element method, and finite volume method. So I'm gonna concentrate on this course here, finite difference method. Later, I am also developing another course, computational finite element method, because finite element method is very helpful for complex geometries and flexible computation. Finite difference method is very historical and very primitive method, and it is widely used. That's why we first introduced this computational finite difference method or course here in this internet. Okay, so what is finite difference method? Finite difference method is a mathematical expression of the form f x plus b minus x plus a. I'm gonna make you understand what does this mean. Okay, if a finite difference method is divided by b minus a, one gets a difference quotient. The approximation of derivatives of by finite difference plays a central role in finite difference method. Here the approximation of derivatives. Okay, so this is very important thing. I think I think I should mark what this the approximation, this one, approximation of derivatives. So what is derivatives? We know the approximation of derivatives with finite difference plays a central role in finite difference method for the numerical solution of differential equation, especially the boundary value problems. Okay, so we know there are ordinary differential equation and partial differential equations here. uh, in here uh, in mathematics or in real life problem, right? So this kind of differential or partial differential equations would be approximated by finite difference approximation, the approximation of derivatives with finite difference method. Okay, how we can do that, we'll see later. Okay, so why we do use finite difference method? Because of several important advantages of this method. Widely used because it is one of the most primitive methods to solve partial and ordinary differential equations. So our ancestors have used this method widely, and so we do have several codes or something like that, and it is very easy to implement and easy mathematics to understand, and no complex mathematical complexities are here, and that's why, and hence as it is easy to implement and have easy mathematical involvement, so hence it is easy to code and we can write code very easily here in MATLAB. Okay, so it is very important. So that's the thing why we do use finite difference method. Even yet now in various scientific fields, scientists feel comfortable with this finite difference method here. Okay, so generally we do solve partial differential equation or ordinary differential equations using the finite difference or numerical methods. Okay, so there are lots of partial differential equations involving in your daily life problem, involving in scientific problems, involving in computational problems. For example, Euler equations, we do know Euler equation, heat equation, Hamilton-Jacobi equation, Hamilton-Jacobi Bellman equation. Heat equation is one of the important problems here because using this equation we can measure how heat can propagate from one place to another. Laplace equation, one of the most important invention in mathematics, because using the Laplace equation we can solve numerous equations. Okay, so here we have also, for example, Maxwell's equations, Navier-Stokes equation. So one of the important equation, Navier-Stokes equation, especially in fluid dynamics or in geodynamics. So we do use this equation for fluid movement or in mantle convection for geodynamics. Poisson's equation, primitification. So primitification is also important for hydrodynamics. Who do use this, especially for civil engineers and who do work with water or something like that, hydrology. Okay, Schrodinger equation, very important equation here. Wave equation, another important equation, wave equation, because wave equation describes how wave can propagate from one place to another through different medium or homogeneous medium or inhomogeneous medium, it doesn't matter. Okay, so there are lots of equations here involving in our daily life problem, scientific problem here. So our numerical methods, finite different method will be presented here in this course to solve this kind of equation in a particular domain, right? So for example, I'm going to tell you about the heat equation. Say for example, this is the domain. Okay, for example, say this is the plate, okay, whose length is up to say called 0 to 10 centimeter it is length, and 0 to say 5 centimeter is wide. Okay, it's width. Okay, so uh, if this is the boundary, and say if the temperature of this region or of this boundary is 100 degrees Celsius temperature, but here all these portions are having 0 degrees Celsius temperature, then how this heat, there is this portion is heated region, right? Okay, so how this will be propagated through this region and will be balanced with time. So we can understand and we can do that using this heat equation. One of the important application of heat equation is the we do use computer laptop that or that enormously generates heat, right? So by the heat equation and numerical problems we can solve where we should put our cooling fan to minimize the heat, because we have to we have to escape, we have to get this out heat from a laptop or computer, something like that, right? So numerical equation can do that. So for wave equation, sir, I'm gonna show you another example for wave equation, how wave equation can help us. Okay, for example, this is a these are globe or earth, this is the viscoelastic material. Okay, say this is the mantle, uh, and this is the core, for example. Okay, so this is the core, this is the mantle, upper mantle, lower mantle, something like this, and this is the crust, something crust. Okay, if there is an earthquake, for example, there is an earthquake. Okay, so how this wave will be propagated from this, so we can understand. And so not only this, how wave can be propagated from the uh, through this region. Okay, so and there are lots of applications of these equations. Here we will see this equation practically. Okay, this is the heat equation in three-dimensional, because we do have x-axis, y-axis, and z-axis. Okay, yeah, and we do have here, like, it is the Laplace equation, and we know that any function, if we take its second derivative with respect to x, with respect plus with respect to y, plus with respect to z, and if we sum that, then it will be the zero. And this is the Laplace equation, one of the important invention in mathematics, because this equation generally helps us to solve the huge a lot of equations. Okay, and this is the Poisson's equation, and this is the wave equation. This is the medium speed of the medium, and in this heat equation this is the thermal conductivity. Okay, and in this equation we can measure how heat can be propagated with time. At the same time we can do that here, we can do the same thing here, how wave will be propagated through a medium with time. Okay, how we can do that. So with time we can see that how wave can propagate it through this. Okay, so I hope you have understand you have already understood what is partial differential equation, what is the application, how these equations can be solved using the numerical methods, especially finite difference methods. Okay, okay, so to understand or to uh, make a concept about the finite difference method, then we have to understand the domain and the grid concept. We must have to have a grid concept. Okay, so what is domain? Domain is nothing but is our real life domain. For example, a car, right? Or for example a rod. This is the rod. Okay, so this is the rod. So you want to see how heat can be propagated. If this is, for example, if this is heated about 200 degrees Celsius temperature, okay, and it is 0 degrees Celsius temperature, then definitely heat will be propagated this way, right? So how heat can be propagated from these portions or this part to this part, right? So this is one dimensional. So this is our domain, okay, and this domain can be two directional. That means something like that, yeah. So this is the plate, this is the two directional, this is the x, and this is the y, right? And it can be a three-dimensional problem as well. Okay, say maybe it is a say maybe it is a car or something like that. Say it may be a three-dimensional, something like that, something like that. It can be a three-dimensional problem domain. So domain is nothing but what our real life problems. Say for example, the it can be the whole art, right? Or it can be a simple rod or something like that, or it can be even car, especially in aerodynamics. Or it can be a car, something like that. Okay, so it is our domain. So domain is nothing but our real life problem or things on which we are interested to work in. Okay, so domain. Okay, grid concept. So in finite difference method we have to discretize, we have to divide our domain. So domain, you already understand the domain. It can be 1D, 2D and 3D, right? So yeah, at first what we have to do, we have to discretize, we have to divide this domain into a finite elements, into a number of discrete objects, a number of discrete squares, something like that. Okay, for example, this domain can be subdivided by several rectangles or several squares. For example, they're two-dimensional. Okay, so if we divide this, we can divide our several this domain by several. Okay, so we have divided this, and we have divided our domain, so this portion by several square or by rectangular portions. Okay, so we have for example say 100 um, 100 element or 100 domain, something like that. Each domain has four nodes, one, two. So, I'm gonna change the color. So each domain has one, two, three, or four nodes. Okay, these are called nodes and these are called elements. Okay, this is called element, or this is called a domain or something, a subdomain of this. Okay, so for each node we have to calculate what is the solution of that partial differential equation. Okay, this is the main theme of finite difference method. So using this, so I'm going to show you about the grid, several grids, how we can do that. For example, this is the grid, this is a domain. Okay, and this rectangular we have subdivided into several squares or something like that, right? Several something. So in finite difference method we have to at first discretize our domain into a number of subdomains. It can be even more smaller or something. If it is more smaller, then we'll have more better accuracy, better accurate results, better solution. Okay, but we have to pay a computational cost, because we do have a in generally for a personal computer or personal laptop, we do not have great memory. It requires a huge memory or huge computational cost. Okay, so I'm going to tell you all about this in later. Okay, so for example, this is a I'm gonna show you grid concept, or what is grid. So we have already said that in finite difference method, or we have to choose at first our domain. Okay, it can be a car, it can be aeroplane, or it can be a plate, it can be a rod, it can be even art. Okay, so it doesn't matter. So which material or we are interested to work in, so that is the domain. So to get a solution, we have to discretize that domain into a number of finite differences. Okay, so let's see, I think my laptop battery is getting in, so I have to put my plugs here. Okay, uh, I'm gonna get some, wait a minute. And okay, so for example, this is our rod. Okay, these are one of the domain, and we have subdivided it into 1 2 3 4 5 6 7 8 9 10. Okay, so for example, this is another rod, something like that. Okay, so for example, this is 0 and this is 1 2 3 4 5 6 7 8 9 10. So for example, this is a 10. Okay, so we have discretized this into 10 subdomain. Okay, for example, if we say this is xi. Okay, say this is xi. Okay, and this, if the difference between in every discretized domain is age, for example this is the age. Okay, and this is also the age. Okay, then so what is this? This is the xi plus age, right? So this is the xi plus age, so this should be the xi plus 2age and something like that, and this should be the x plus 3age, x plus 4age, x plus 5age. And similarly we can get, this is the x minus age. Similarly we will get x minus 2age here, and we will get x minus 3age here, and so on, right? And so on, we'll get this and we'll get this. So this is the way how we can discretize this. So this is the grid concept, right? I think you have understood this. So if this is the xi, is this the x, then the next point would be the xi plus uh, xi plus ace, okay, I ace, xi plus 2 ace, something like that, and xi plus so x plus 3 ace, something like that. So we can write down here x, say not xi, say x, okay. So we can general formula is x I ace, right? And I is here 1, here 2, here x equal to 3 so in this case we can write x minus I is, okay, I is minus 1, minus 2, minus 3, and so on, something, and I is 1, 2, 3, 4, and something like that, okay. So we can discretize our domain into this way, and I'm gonna show you more more in the following lecture, okay. So in this lecture I'm gonna try to make you understand what is grid in one-dimensional, two-dimensional, and three-dimensional. Okay, so these are two-dimensional grid. Okay, and this is the x-axis, for example. Definitely, this is the x-axis. Okay, and say it is a this is the y-axis. Okay, so in two-dimensional, we'll get, for example, this is the x. Okay, if this is the x, and the difference. In y-axis, the difference between two node, these are the node, okay, and I've already said these are the node, okay. So difference between the two successive node in x-axis is y, and difference in successive y-axis k, for example here in y-axis, okay. So not k, okay. So if this is x, so definitely this should be x plus 8, right? And this is x minus k, okay. And as it is two-dimensional, so we have to put our y value as well. For example, this is y, so if this is y, then this should be y plus k, and this is the y minus k, right? So what is the node value of here in 4 points here? So you can write here x plus x plus ace comma y, because y value is fixed here, right? So here it is the x minus 8, y value is fixed, right? So in this domain, okay. So what is the value of here? X should be x is remain fixed. So y plus a, y plus k, and this is the, here also x is fixed, so y minus k, right? So we have four values in two-dimensional. We have four, we in two-dimensional we'll get the four nodes around a node, okay, in two-dimensional, if it is x-axis, something like that. So how this increment, how it is, if x and k is equal to same, then definitely uh, h and k, h and k, if h and k is equal, that means if it is one centimeter, and if it is 1 centimeter, then definitely yeah, the same value will be occurred, okay. Okay, I'm gonna show you in three-dimensional what, because our realistic, our many problems are involved in three-dimensional problems, and this dimensional problem, I've got this image from this Google Images, because I have to use the references here, okay. So if it is a problem, for example, if it is a domain, if it is an interested domain, here we want to interest to calculate our problem, okay. So we'll get 6 nodes, 1 2, again this 3 4, okay. For a surface, okay. 1 2, okay, this is the surface, right? Two-dimensional surface. In two-dimensional surface, we have already seen that we will get the 4 points. So 1 2 3 4, but it's a three-dimensional, so we'll get another 2 points here. So this is this two surface, okay. So we'll get another here 5 and 6, so we'll get a six nodes around a point, around a node in three-dimensional cases. Okay, so these are the things, this is the grid concept, we have to understand all about that. And if the, so if this is for example x y z, x y and z, then we will get this point is x plus ace. If ace is the difference between two successive nodes in x-axis, for example these two successive node in is ace, okay, then x plus ace, x plus ace, y remains same, z remains same, okay, and it should be x minus ace, y is fixed, z is fixed, right here in this point. Okay, but here x is fixed, y is also fixed, z minus, say for example distance between two successive nodes in vertical axis is k, is l, so z minus l. Okay, so this is the node value or node coordinate system, something like that. Okay, so I think you have understood all about the grid concepts or domain, something like that. Okay, so you'll see now. So this is all about the grid concepts, all about the domain or something like that. Okay, so I hope you have already understood. No, you have already understood that what it was, right? Okay, thank you. I think you have already understood all about this, and I think you have got all the things, because then in the next lecture I'm going to show you about the basic theory of finite difference method. And because we have to approximate this equation, and we have to replace these equations by a finite difference approximation. So what are the finite difference approximation? You will see that later. Okay, I'm gonna tell you something about, this is the second order differential equation, right? So mm, this is the second order, this is the first order, right? This is the second order. So how we can write this second order or first order equation by a finite difference method or finite difference approximation? We have to replace these derivatives by the finite difference approximations. Okay, we will write later. Okay, so we will have to transform this equation to finite difference approximation, so that we can solve this using the finite difference methods and using the grid and discretization. So what are the steps involved here in finite difference methods? Number one, we have to choose our um, uh, at first we have to choose our domain, right? What is the domain? So at first we have to choose our domain. Okay, at first. Okay, number one, this is the uh, this is the one. Okay, number two, we have to discretize our domain. So we have chosen this grid, then we have to discretize our domains. Okay, so how many subdomains will be there, and then on the basis of subdomains we will have our node values and number of nodes here. Then we have to approximate our equation number three. Then we have to approximate our uh, differential equation into finite difference approximation. This is the number three. Okay, then we have to, then we'll have uh, we'll have a numbers of equation depending upon the how many nodes are there. If there are, for example, uh, here we have many nodes, for example 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. We have 1 2 3 4 5 6 1 2 3 4 5. So we have 30 nodes here, right? So something like that, we have 30 nodes here, and we have to solve this finite difference approximation. So this is not the equation, but this is the original equation, and we have to replace this equation by finite difference approximation. Okay, so and finite difference approximation. So we'll have this kind of finite difference approximation equation. So then these finite difference approximation equations will be solved in each node. So we'll get 30 equations, right? So we have to, we'll have 30 equations, something like that. So we have to solve this 30 equation using the matrix, because we know these are the matrix form. Okay, so this is the way how we can solve the partial differentiation or the ordinary differential equation using the uh, finite difference method in a particular domain. It can be a 1D, 2D, or 3-dimensional. Okay, so thank you very much. This is our introductory class, and I hope you have understood what I mean to uh, this courses. Okay, I hope I'm gonna okay, see you all in next lecture and finite difference theory 1. Okay, thank you very much.